Okay, hello, welcome. And let's start. So, what I want to say, uh, you remember that we have constructed two ways to have toposes. So, one was sheaves, the other was H sets for some complete, I think, algebra H. That I won't recall what they are. But the point is that I said that we need three. Sure. Yes.
I didn't completely understand the intuition behind the equality. Each of the sets is equipped with this relation R.
Exactly.
And so why isn't it? And then there's also independent existence, right?
Yes.
Why is it? Why should the set tell us what is equal and what is not equal? That's not great.
Yeah. So there is some sort of philosophy behind it, and the philosophy is how to explain. Okay, from the very philosophical point of view, we live in the realm of constructive notions of sets, right? And for a constructivist, a set is not just some object that some collection that you can have, right? It you construct it, and also you have to construct everything related to it, including the equality, right? So there's no universal equality, if you like. Any equality is just restricted to a domain, and therefore it should have be given. But if you want something very mathematical, a mathematical description would be that let's say that you have a set, and then you want to change the value of everything to live inside H. The very primitive thing that you have to evaluate is equality, right? So from your language, and therefore equality must have some kind of value inside H, or does that thing, right? But if it helps, let's say that you don't want just simply a set, you want some structure, then it is not just a set plus some equality, it is a set plus equality plus some other relations, but all the relations do the same thing as equality. They read elements and then they land in H. And I have simply equality because I live for on a very basic level of just a set without any structure. So we saw these two categories. I said that we need another one, the third one, but I won't explain it today, later, probably next time. The list is not exhaustive, it is just my choice, but it kind of covers different flavors in a very comprehensive way, if you like. And also we saw that this is just equivalent to sheaves on H. So actually it is a subfamily of the first family, but the better, more logical behaved family. So now today I want to talk about the independence that I promised, at least some of them. So to do that, I have to say, because how to prove some independence? You have a theory, let's say some sort of first order theory, and then you want to show that you have a model of that theory, which is not a model of some sentence, right? So the first thing that you have to learn is that if I have a topos E, and oh god, and if let's say that it can be just this or that or whatever, right? But any abstract topos that you can have, then how to interpret a first order language, say, inside these guys, right? Because we have to be able to do that first. If you remember, we had something about some very limited fragment of equality and conjunction and top, if I remember correctly. Not in the topos, in any category with limits, with finite limits, right? But what I want to say is that if you have a topos, you can do far more than that. So you can first interpret the whole first order language and even more. So what do I mean by first order language? We all know what first order means, but the one important point for me is that actually it is better to present everything with multi-sorted first order language, right? So what I have is just some sorts. Can be an infinite set of sorts, right? And therefore, when I write quantifiers, so they should be in sorts, right? Something of that sort. If you don't like it, just simply think that I have just one sort, sigma, and everything is just relative to that one sort, and I don't write it down, right? So how to interpret then things? Let's say that I have E, and then if E is a set, we know how to interpret first order language, right? So whatever language you have, let's say that you have a language, you have some function symbols, you have some relational symbols, probably PIs, PJs, right? And always I have equality. This is my assumption, right? So how to interpret these things? In set, we pick just one set, right? These are functions over those sets. These are relations, subsets, etc. And if you have different sorts, then for any sort, you pick a set, and then you do the same thing, right? So here, when E is a topos, any topos, if I want to interpret things, I assign to any sigma I some object AI, of course, that is my set. Sigma is a sort. So you have first order, multi-sorted first order language, you have some sorts. To any sort, assign one object. And to any function symbol, assign just a map, right? So for instance, if I have one F that reads two things of sort sigma and tau, and then the whole thing has the sort rho, then simply interpret it as, so F must go to what? To the interpretation of F, if you like, and it simply goes from the interpretation of sigma. And if you have multi-sorts, just use this. And these are objects. This is a morphism inside the category. So I can do it for any category besides, right? What happens to these PJs? So if I have some PJ, some P like, yes, I have a function symbol F. With P. It's rho. So you have a function symbol F. It is multi-sorted. Therefore, you read two things, one from sort sigma, one from sort tau, and rho is the type of the output, right? So it is the interpretation of the function symbol. And these are the interpretation of so that the guy here is just the interpretation of symbol, right? So that's easy. What happens to P? And also including equality. So P is, let's say that P reads just two things from different sorts, right? So of course, then the interpretation of P should be what? Should be a sub-object of this times that, right? So therefore, it is simply a sub-object of the interpretation of sigma times. There are some subtleties that we have to keep in mind. So one is, for instance, the order. So I'm using some fixed order here, right? But there's no reason that X comes before Y, right? It can be anything. But come on, everything is up to isomorphism is the same. So Yes. So atoms equality should go to equality really. What do I mean by equality? So equality, if since it is just you know a predicate should be a sub object from sigma. So of course any type has its own equality, so it should be a sub object of this, and there is one canonical sub object of this guy, and that is what? That is just this, right? So from this, you can go to sigma two ways: projection first, projection second, and then you may have this guy as the equalizer. I have all the limits in any topos, therefore. So that's the interpretation.
Your interpretations are the morphisms or the equivalence classes?
The equivalence classes. But really it doesn't matter. So then what happens to conjunction, disjunction, etc.? So here I cheat. Actually, if you think about it, I never said anything really in topos theory for you. So what we had was simply just some basic things plus some topos construction. We had nothing about topos theory. Topos theory starts when you pick a topos with that axiomatization and prove things. So we never did that. But I can claim things, right? And one of the things that I claimed is a theorem, if you remember, that for so if E is a topos and say A is object of E, then sub in E of A is a Heyting algebra. We saw it so many times. Of course, I never proved it. Probably I should have, right? Using just the axioms of topos theory. But in any special case, somehow we have to compute it at some point. We didn't. Today we do it for 8 sets. And at some point we do it for sheaves. But if we don't do it, so it does not help us simply because you want to interpret really things via the Heyting algebra structure, conjunction, disjunction, implication, and you want to know what it is. So you have to know the actual computation of them for any actual topos. So see, here I'm saying that how to interpret equality. It's a predicate. It should be a subobject of sigma times sigma, but it is not any subobject. It is the subobject, and that the subobject is defined like this: that you go from this to sigma via projection first or projection second. Yes. So, okay. What do I need this Heyting algebra structure for? Of course, to interpret the propositional things, right? So I want to interpret top, I want to interpret bottom, I want to interpret conjunction, disjunction, implication, right? And I can't simply. Why? Because you start with your predicates, and probably I have to also mention that I did that million years ago. That so it is simply just the interpretation of the predicates. What happens to terms if you have this and say, I don't know, S of the right? So what is substitution? It is just simply pullback along the obvious map there, right? Because this is it clear or not? Yes, that's the point. For that, I have to write down things. So let's say that I have some Px sigma to simplify things. And then also I have a term. So let's say y. And I have a term t of x. And x is, let's say, of type sigma. and I want to substitute this guy there. And after the substitution, I get P T X X sig, right? So this guy is interpreted as what? As a subobject of tau, right? Okay, fair enough. Here I want to have a subobject of what? A subobject of sigma, because after I substitute things, then I have just one variable x, and therefore it should be a subobject of sigma. So the interpretation of this px, good, sorry, t of x sigma, interpretation of it should be a subobject of sigma, right? And then there is one canonical map. Any term can be interpreted by the composition of the morphism as a map from sigma to tau. So that is then the map sigma to tau, the interpretation of T, right? So what I'm saying is that this map is pullback of that along this T, right? We saw that before, but that doesn't matter. So therefore, I have the interpretation of all the atomic things, and then I need some propositional structure to interpret more complex things, like the conjunction, disjunction, implication of things. And the Heyting algebra structure that I didn't explain simply helps us to have that. We can interpret these things. Why? Because let's say that, just as an example, so if I have Px, so I don't write the types, disjunction Qx, right? So then this is when you interpret P, so that the interpretation of this should be the interpretation of Px, the interpretation of Qx, and these two guys live in sub something, the source of the variable. And then I'm saying that sub of anything is just a Heyting algebra. Therefore, you have the disjunction operator between them. So interpret disjunction as disjunction, conjunction as conjunction, implication as implication. And the Heyting algebra structure simply says that any propositional intuitionistic argument is valid, right? So if I prove something from something else in a propositional way, then that thing is just valid in my topos because I have the Heyting structure, so I can validate the intuitionistic. Not necessarily classic, but intuitionistic I can understand. That's not first order, it is propositional. And that's fact. So I have to say then something about first. So how to do it? For first order, you need another theorem, because simply I'm just, claiming theorems. So E, let's say, is a topos, and AB are objects. Then first, we have, maybe I have to explain here. So we have P0 from this guy to A, and we have these are projections. We have these two maps, right? And then we have also the pullback of these two guys as functors. We have seen them. That goes the other way. So if you have something subobject of A, pullback becomes a subobject of A times B. So it goes this way to sub A to sub A times B. And the other the same for B. So what do I mean by this? So this simply says that if you have a subset of A, you can pretend that it is a subset of A times B. So that's just the usual idea that we have phi, say X, of some sort. And then, and this means that, you have the variable x free, but you can also have the same phi, but you can pretend that you have the free variables x and some y, right? This is just the same idea. So this map simply does nothing except that it pretends that you have more variables, right? Adding dummy variables. One thing. The other is that quantifiers are the best way to come back in both directions. Technically, they are called adjunctions, but I don't want to bore you with adjunction. So what I'm saying is that then there are functors, let's say for all p, going from sub a times b to sub a, and also exist p, two of them, such that you have this equivalence. So if I have that is the same version to write this. So if I have some a that this lives in sub x times y, this lives in sub x. So that's somehow fancy thing. And so P is just the projection on the first. So when I write P, simply I mean P0. Right? Too simple. So what I'm saying, you have two objects. You have the obvious projection, right, from x times y to x. So I made it from x times y to me explain. So the idea is this. So you have x times y to x. That is the projection P0 or P, right? Then we have this P star thing, this P star, as a functor that goes from sub x to sub x times y. We saw that it simply reads something as subset of x, and it pretends that it is a subset of x times y. Then this guy does the converse in the following way. So I'm claiming without any proof that I have this functor. And then what does it mean to have a functor like this with this property? Simply it means that first B, okay, let's go here. B is a subset of x. A is a subset of x times y, right? So let's write them as formulas because then it is easier to see. So you have A of x, right? And y. And you have B of what? B of x, right? These are the two things that I have. These are sub-objects, A of this, B of that, right? So you can read them as some formula. Then what I'm saying is this, that P star of B simply is just the same of Bxy, but you pretend that you have also the variable y, but you don't. Then the maps between the two, simply because they are sub-objects, it means that this is less than that. So I'm saying that A then is less than Bx. This is equivalent to this. There exists P A xy is less than B x, right? So that is the categorical version of this kind of equivalence between subsets of formulas. And now you can see that this is really the quantifier. So we usually write this as there exists y, a x, y, right? That is the existential quantifier.
The quantifiers, you say that they are functors. They are functors within which categories?
The posets of sub-objects.
That's all.
Yes. So exactly. So you can think just not just functors as monotone functions. So we have monotone functions with this property. And the property simply is just the rules for existential quantifier, right? So the rule for existential quantifier simply says that if you prove this from that, but you know you have no y here, and the way that we make sure that there's no y here is that b is from sub x, but you pretend that you have also y. So then there is no y. Therefore, you can introduce your existential quantifier. And if you have the existential quantifier, you get it back simply because A proves it, right? Therefore. So that adjunction technically captures the essence of existential quantifier, right? So if I want to write down what is existential quantifier in the categorical language, I have to say that do this, do the projection, pull it back, meaning that you are adding dummy variables, and then find the left adjoint of it. The right adjoint is the other quantifier. So, so the theorem such that this and also I need this a similar thing for what? For all. Home again of this time, let's say C and D is the same as home CD. But then this time I have to add my P star here and for all P here. And so therefore, this is sub X this time. This is sub XY. So again, if you think about it, what does it mean? D has two variables, right? So I have my D this time here with two variables. I have my C with one variable. So that is then C, right? And here I have for all PD of XY. And here I have C of X. These are the quantifiers for the universal quantifier rules, right? Again, C has no Y. If you prove something with Y without any Y here, then you prove for all of it. And conversely, right? So again, this is the categorical version of the universal quantifier. So this is, universal quantifier is whatever that satisfies this thing, and it is unique. You can see. So what I'm saying simply is that the obvious candidate for universal and existential quantifiers exist. But the difference between this theorem and that theorem is that theorem is local. You have one object, you have sub of that, and it's a Heyting algebra. But quantifiers is the interaction between different sub-objects, right? Because you change your number of variables. Therefore, you have this, right? If it seems somewhat abstract, it doesn't matter. So we can see the examples of them later. Again, I'm just saying that it exists. I'm not proving it, right? But then it means that I can use these two guys also to interpret quantifiers, right? First order quantifiers. And since I have this thing, or if you want this equivalence, then intuitionistically, again, because these are intuitionistic rules, not classical, intuitionistically, we have the full first order interpretation of the language, right? Sure.
Theorem says E is a topos and X, Y are objects of this topos.
Yes.
And they are functors, and are the functors exist P for all P? These are names for functors. Right?
Yes, yes. Index.
And then there's a right.
And this is the property of the functor.
Oh, and they depend on the P, which induces this P with asterisk.
Yes.
But then, okay, but the P with asterisk, it is already arrayed, but you could see that it is from. All right. So P asterisk is from sub X to sub XY,
Yes.
and these exist P and for all P are from sub XY to sub X.
Right. So the picture is like this, that you go from sub X, as you said, to sub XY, right? That is your P star. And then you have this, this, and you have that.
So there's this thing that limits and colimits are adjoint functors to some diagonal map or something.
Yes.
So does this tell us that the existential universal quantifier is the supreme and if you move in some percent?
In some categories, yes. So
Okay, but is this P star the diagonal map or no?
No. So the point is that adjunction, limit, colimit, universality, all of them are the same things, assuming that you are changing your category in the right way, right? So this is adjunction, really, but if you want it to really be limit, then you have to change it a bit to be another diagram in another category. Okay, but in some sense, you can say that this P star is just a way to read something with one variable and pretend that you have two variables. And these are the best way to kill two variables to one variable, either with universal or existential quantifiers. So it is like the least and the greatest kind of thing. So no, not the whole of it. But of course, it is not available in any category. So if you have the whole thing that I said, it's called the Heyting category. So by definition, it is just a category with all the structure, all the Heyting algebras and all these things. And then any topos is a Heyting category, but topos is more. So and we will see how a bit later. So okay, fair enough. So if you have probably, therefore, I can interpret the whole first order multi-sorted first order intuitionistic logic, and if you in a sound way because of these things, and also it is complete. I have to say that if you interpret everything in any possible topos, then it is complete. But it is also possible to pick one topos, but that topos is not set, for instance. So because if I interpret everything in set, right? If I pick E as set, then everything is classical, for instance. So it cannot be, complete for intuitionistic. So okay, that's it. What should I say? Maybe for H sets, later I say how to interpret these structures, the quantifiers and the Heyting structure algebra for sheaf category. But for H sets, I can say it just now. It is kind of easy. So the point is that to any formula, as you saw, to any formula with some free variables, we assign a subobject. A subobject here in H sets is simply one H subset. We saw it last time. So it is. So when I say that I have formula phi, say X sigma, then the interpretation of it, by definition, was what? Was a subobject. It's a subobject of what? Of this. So the interpretation of sigma. But then, since we live here, it is just equivalent to one H subset. Therefore, the interpretation simply is a map from this to H. So simply it reads one element of the bigger H set, and so this is just a value of being inside or satisfying phi, right? So then, if you read everything like this, with fixed sigma, then it goes to H. Then all the Heyting structure is easy. Just do it pointwise. So for instance, if I have phi here as the map, and also psi, question is that what is phi or psi? It is simply the or of the things here in H, right? It's easy. So the whole Heyting structure comes from this guy. 1, 2. But we know that it is complete. The completeness helps these two guys. So what is the interpretation of for all then? Let's say that my phi is just based on xy. And therefore, if you write it down, it would be something like sigma times tau to h, right? And what is then there exists p phi? It should be something from h, and I have to kill y. Therefore, let's say that from sigma, right? What is it? It is easy. It is just the exist of something, right? So therefore, the value simply is, this guy is, there exists some y inside, so such that this. Right? And I can write this down simply because I have the big disjunction. And for all is big conjunction. I have to prove it, right? Because these are not arbitrary. These are exactly the ones with this property, and they exist. And therefore, you have to find them, and you can find that they are equal to this, right? There is just one true notion of universal and existential quantifier. In this case, they are reduced to this big disjunction, big conjunction, right? Okay, so therefore, at least this is the reason why H sets is good. Because if we live in H sets, and we have a formula to interpret it and find the values is just kind of easy, right? Propositional lives in H, quantifiers are big disjunction conjunction, so that's just easy to work with, right? We will see something about the sheaves later, the general setting of sheaves, and then you can see that it is not that kind of obvious. But anyway, so now I can interpret everything in first order language, which means that you can use it to prove independence, right? Let's say that I have some first order language, some theory, then I have to interpret it in some topos, let's say H sets or whatever. And then if you do it, then probably you can construct some models. And if you use H sets, then probably your model construction is not that hard, because everything is kind of easy to compute. Okay, fair enough. But what I want to say is what? Before going any further, I have to say that since we are working with toposes, we have more structure, not just first order. We have also higher order, right? So first order means that your quantifiers are over sigma and tau and etc. But let's say that what is higher order? One interpretation of higher order is that you can go over functions. Let's say that all functions from sigma to tau. Can we have this? Yes, because we have this guy, right? We can interpret this sigma implies tau as the exponentiation of sigma and tau, and you have exponentiation in two process, and then the rest is just first order again. It is just interpreting one quantifier inside one object. You can simply pretend that it is a new source, right? 1, 2, even more, probably you can say that for any predicate inside P of sigma, power set of sigma, also you have this, right? Because power set in two process are just all sub-objects, and all the sub-objects is just simply the sub-object that sigma thing to the sub-object classifier, right? No, sorry. Right? I have one object storing all the subsets. Therefore, I can just have the quantifier over there. So I can talk about higher order things, all subsets of subsets, etc. Right? So it is really first order, but since I have more structure, then I can talk about function spaces and the space of power set. Right? Okay, I don't need them right now, but it's worth knowing. So how to prove some real independence? Probably I have to explain something about some model construction, at least for, you can just fix your, H or B if you like. It could be Boolean algebra, right? Then everything is classical. And then you pick some H set with enough structure, and then you interpret your rings or, groups, whatever in the usual first order language. But probably more complex setting is arithmetic, right? So you can interpret arithmetic, for instance, in this setting. How? One canonical model is this that we have seen before, and I want to emphasize today. So pick this. So let's say that I want to interpret arithmetic. Arithmetic is one sort, right? Therefore, I need one H set. Or since I want everything to be classical, one B set, probably it should be Boolean, right? So let's say that I have to have some B and some B set, right? Such that you have induction, you have the obvious axioms, etc. So the canonical construction is this. You pick some set. So this is example. You pick some set I. This is a set, any set. And you set your B as the power set of I. So of course, it is Heyting algebra, it's even Boolean algebra, right? Complete Boolean. Then your B set simply is N to I, and the equality, probably I have to write like this. This is my R. It should be what? It should be, we saw this guy before, if you remember. It should be between two elements here. So elements are alpha and beta, two sequences, right? With indices in I. So, and it must land inside B. It should be a subset of I. And what is the definition of that? The definition is simply the set of all I's such that all equals, right? So my natural numbers now are not just one number, it's a sequence of numbers indexed with something. And then therefore the value of equality is not just either equal or not, it is the extent to equality, and it is just a set of all I's where these two guys are equal. It is easy to see that it is a B set really. And so just to talk about arithmetic a bit, how to interpret arithmetical things. First, you have some function, right? Any function symbol like plus, sum, successor, whatever. These should be morphisms here. And the obvious morphism is what? It's just composition, right? With addition and multiplication and whatever. So for instance, successor should be a map, right, to this. And what is the obvious map that I can propose is just read alpha and then construct successor of alpha, right? In any I, alpha I plus 1. Do it point by. And then the same for addition, multiplication, etc. And then you have to show that it respects equality. And respecting equality simply means that if two things are equal, then the successor of them are equal. And the same, right? So that's kind of obvious. You can interpret everything, and okay, but it is not the end of the story, right? So I have to be able to evaluate the truth value of formulas. How to do this? So this is just kind of too easy because you can evaluate the value of everything. So if you have a formula phi with some, n1 up to nk, these are parameters, this guy must live in pi. It is just the value of phi by definition. And the value simply is all the i's such that, so this is what I have to prove, such that this guy is actually true in n. You pick all the i's. This is just the wash style kind of theory, right? So how to prove it? Just induction on phi. That's easy, right? Because equality is like this, and then the rest is just the consequence of the way that we know how to interpret things in 8 sets, right? Because if we want to interpret conjunction, it should be intersection here. Disjunction should be union here in pi. Implication should be just the usual Boolean kind of implication here between sets, etc., right? And quantifier should be just big conjunction, big disjunction, etc. You can just play with this structure simply because you know how to compute the structure, and then you can prove this. So usually people don't do this kind of thing, right? They work with ultra filters. Ultra filter is just something simply because you don't like your Boolean valued models. You like just to have 0, 1 valued model, the usual kind of model. You have to quotient, and ultra filter is just there to do the quotient, nothing else, right? If you allow yourself to have more complex models, then this is just this. Right? Okay, but
H, like H and Y and H2, and then you have some isomorphism, you can just move the whole H sets to the H1 sets to H2 sets.
No, one way. So if you have something really positive, then you can move it. But implication for such, it depends. First, what is the morphism between Heyting algebras? If it preserves everything, then you can move everything. But then truth goes backward. So because the interpretation is the same as the f of the interpretation, but then it should be 1. But f of something is 1, it doesn't mean that the thing is 1, right? So there are some subtleties. Your f should also reflect things. But anyway, so that's the main idea, that you can move between.
Algebra and 2, and you have the morphism.
Yes, exactly. So that is just the idea of ultra filter, right? But it is not useful. That's just a very dumb example. The reason is that if phi is true in n, then this is just a whole set I, and therefore the value of this is 1 in pi, which is just a whole set, the biggest set. Therefore, if phi is true in n, it is true here. And if it is true here, then it's true in n. So they are equivalent. I constructed something very equivalent to n. Probably the good thing about this is that it has some non-standard elements, some very big elements that are not from n. For instance, in the sequence here, you can define the sequence. So you can pick your I to be n itself and define alpha n as n plus 1. So the standard elements are alpha m such that it reads n and it's the constant ones, right? The constant ones are the 0, 1, 2, 3, the usual finite ones. But if you have just something with a bit growing power, then it is non-standard. So probably the only use of it is just to construct non-standard models, but not really equivalent, of course, to it. The things got more interesting when you observe that, come on, to have one B set, you have to handle your equality, right? Nothing else. And therefore, I can just simply erase this guy and substitute it with some f as a subset of n to the I, right? With the same thing, of course, you restrict, right? It's H set, it's B set. But then there are some problems. The problem is that you cannot interpret your arithmetic, the language, simply because, so if alpha is in F, then S O alpha is not necessarily in F, right? So it should be closed under successor and closed under addition multiplication. And if it is, then it means what? It means that I can interpret the basic language of function symbols inside my arithmetical language. 1. 2. The problem is this. Then this guy is not true necessarily. Why? Because if you write down the proof, you see that when you have quantifiers, okay, when you don't have quantifiers, everything is fine, right? Because the atom is the same, exactly, equality. If the atom is the same, the conjunction, disjunction is just, and or, it's easy. Implication, negation, everything is easy. So for any quantifier free formula, you have still this guy. But if you add quantifiers, you have some problems. Because then the big conjunction is not over all sequences that you can play with. It is just a big disjunction or conjunction over all sequences in F. And they are restricted, and therefore you cannot capture the whole thing. Probably it's a bad thing, but not really. It's actually a good thing. Why? Because then I can construct a model, kind of arithmetic, such that is that equivalent to n. It is equivalent for all quantifier free formulas, right? Because of the same kind of reasoning, but not probably for more complex formulas. So if I want to kill something more complex, right, in arithmetic, prove something independent, then I have to use it. For instance, probably it is interesting to see that actually this model for any f with that property, closure property, I mean, say on n to the I, this is always a model of I open induction. So whenever you have open induction, it is valid here, right? And the reason is this, because what is open induction? If I write the formula of open induction, it is just A, so let's work with phi 0, and for any x of type n, I don't write it. Right? This is induction, and phi is quantifier free. Therefore, it's called open induction, right? So that guy is valid in my model. I have to compute its value, right? So I have to prove that this value is 1, and 1 here means the whole set, I. So everything is here. So I have to show that for any I is here. And how to do that? So if you open up this implication, then you see that you have to actually prove this. Phi 0, conjunction, big, this x's goes to alpha in f's. This is just a classical kind of implication. And this should be, since any I is here, this simply means you have this. I'm simply opening up everything, right? That's the meaning of the validity. I have to prove this. I interpret quantifiers as these big things, and then the rest is just the same. And how do I know that? That is not that hard. So if you want to prove that something is in the big intersection, it is enough to prove it for any alpha, for any random. So how to prove this? So the point is, how to prove this one? The point is that I know what it is. This is quantifier free, and therefore it is just a set of all i's such that n says that phi of alpha I is true, right? By that kind of argument. So that was my, sorry. That's just my ugly mistake here. So these guys come from alphas. And here it means alpha 1i up to alpha ni, right? Because one should be in n, the other should be for sequence. And then I have to show that I have this. So that guy is a subset here. So let's say that I is here. I is also here. And I have to show that I is here, right? So if I is here, then phi of 0 is true. If I is here for any alpha, phi alpha implies phi alpha plus 1. But the point is that alpha I is a number. It's just one number, 5, say. Therefore, you can start just from 0 and then go 1, 2, 3 to 5, right? I'm reducing this induction to the usual induction. Using the fact that I know how to compute this, it is this, right? Very easy. So I have multiples of I open. So that kind of thing, probably up to the quotient for ultra filters, because we don't like the PI kind of things. It's called restricted ultra power. And it's a very powerful method to prove, things in bounded arithmetic. Jan has a book about it, right? The forcing with random variable book. And also, if you are clever enough, you can kind of choose your F in a very sophisticated way to prove something beyond I open. So I guess the first non-obvious kind of use of this was from 80s, I guess, if I remember correctly, by Kripke and Cochin. And they use this kind of construction with some very sophisticated F to construct a model of PA even, not I open, and show that the Paris-Harrington theorem, that Ramsey kind of thing is independent. But the point is that you have it for any bounded kind of fragment. Therefore, you have to pick your F as big enough in a way that everything is bounded somehow with something in F, and therefore you have induction. But also your F should be in a way to refute the that Ramsey kind of theory. So there are many interesting things about this construction. But I won't say more, probably. This is just one example to know how to play with this game of using B-sets. The real independence, however, is somewhere else. So before going somewhere else, I have to say that, as you see, we can use these toposes and specifically these B sets or H sets prove something about first order kind of theory, right? Like arithmetic. But what about set theory? There's a problem there, right? The problem with set theory is what? So the problem is that, so based on what I explained, you pick your topos, and then as long as you talk about some sorts, finitely many sorts, like numbers and reals and blah, blah, you pick your sorts as objects here, as some sort of structure objects, as not structure sets, and then you evaluate everything as the sub-objects, etc., right? problem with set theory is that set theory needs the whole structure of E, not just some sets, all the objects. And if you think about the quantifiers in set theory, for all x and there exists x, these are not referring to inside of a set. These are universal over all possible sets. And that's a problem to interpret set theory in toposes, right? I cannot just use one object. This x refers to all objects at the same time, kind of. And I don't know how to interpret that. The arithmetic is that x simply means x inside some n. You pick your n as the word of numbers, and then the quantifier goes there. It becomes local. It is bounded somehow. But the quantifiers for set theory are not bounded. They are, because they are referring to not just elements of some set, they are referring to all possible sets. Of course, you can interpret it like that you have a big model of set theory and then everything is there. But then just the assumption that you have a big model of set theory is kind of the main thing that you want to play with, right? When you want to prove independence.
So it can count it up.
Yes. There are, of course. I guess I said. No, the point is that, okay.
Why is the model of set theory worse than the model of
The existence of, how to say it? If I want to construct a topos with one object in, I can construct a topos with one object inside it, which is a model of set theory, just like any other first order theory. The problem is that then the assumption that such a topos exists is kind of, big. It is just too powerful. I don't like it. I want to transform my topos, not just one object of it, as my new set theory, right? Because any topos should be a set theory, right? Because any topos is not some arithmetical word, it is just a set theoretical word, right? If you have a set theoretical word, one object of it, okay, think about set theory in just a very naive usual way, right? You have some collections of sets. When you say set, it could be anything. When you say numbers, they are just elements living somewhere in one set, right? You can solve this conceptual barrier with going just bigger, right? But that's not the way that we really think, right?
Is it that there's some operation you want to use in your set theory that doesn't work very well inside this single E, but works better between on a large scale and not the case within?
Yes, probably. The link is that you designed your topos to be set-like, right? There are sets, H sets, etc., right? So then all the guys together with their product, exponentiation, blah, blah, all together behave like set theory.
If you have those things, you have exponentiation.
Yes. There's a difference really, right? So the difference, come on.
This E is made to resemble set, the category of sets. It has single E. A single E is made to resemble the whole category.
So E is the object in this.
No, E is the whole category, the whole topos.
So how you can interpret logic for structures living inside, like for not to say that for example the category set itself I'm not satisfied from the hypothesis.
Okay. Well, but it's suggesting there's two ways of building a model. One is by an object in the topos, and the other one is by the whole topos.
Yes.
And you're saying one is appropriate for arithmetic and one is appropriate for set theory. But I don't know what you're saying why.
No, I'm saying that both are available. No, the one object thing is available for every first order theory, including set theory. But of course, you don't want to do some blind kind of thing, right? So for instance, if you want to construct a model of arithmetic, I pick my n from set, I change it a bit to become a new model of arithmetic. So let's say that I want to do the same thing, right? So in set theory, I have no one set. I can, but probably I don't like that you pick just one set as a model of set theory, right? When you want to interpret set theory, you interpret it as, you know, the language between all the sets. And therefore that I can change, and I change to become my topos, right?
I mean, if you're doing set theory, you don't normally pick one set that you don't want to set. You're doing topos theory now.
Yes.
Right. Are you saying you're actually only going to decide set?
Of course.
All right, carry on.
Yeah, of course, it is meant to be some sort of alternative set theory, right? Okay, so the problem is that you have quantifiers and they are unbounded and you don't know how to deal with it. So there is a trick. The trick is that you use ordinals to construct the hierarchy V alpha for any alpha in ordinals. And ordinal, I mean outside the ordinal. So this is not the only problem. I'll explain another one, which is kind of important.
Outside.
Huh?
What's outside?
We leave outside in, you know, in meta theory, I have some sort of set theory. There are ordinals there. So I construct my V alpha in just in the usual way. So my V0 is just the zero object here. So every V alpha is object here. So V alpha plus 1 is just the power set of V alpha. Therefore, it is just omega to V alpha, right? All the power sets. And then the rest is just the big union. Assuming that E is complete, at any time I can construct the big union thing, right? And then you construct your hierarchy, and whenever you say for all x, you really mean that first interpret everything as for all x in V alpha for some alpha, and then do conjunction on all alpha, assuming that everything is complete, right? So that's the trick. You
This
do.
is a complete condition, there's no size bound.
It has the size. It says that for any set like thing, then the limit exists or the co-limit exists. Huh? We all.
That's a conjunction over all outside ordinals.
Yes. Yeah, you are right. Does it matter really? Because it's a class like really. That I don't know. You are right, probably.
Maybe you can just inaccessible cardinal to get it, and then you will have the set of animals.
Yeah, that I can do. That's simply like so. So the equivalent to theoretical version is that you have universes, etc. Right? You can do that, but I'm just trying to do it without any big assumption. Probably I can't.
You shouldn't, because otherwise.
I shouldn't. Yes.
Outside in your world, there would be without any
Assumption, yes.
models and theories. You can.
Yeah, not really, because you have a model of set theory that controls your E, right? The whole construction of E lives inside a big set theory outside.
Well, yes. So you're already assuming such a model exists.
Yes. And I don't want to assume a big model to construct small model, right? I have the feeling that if I have a model, based on that, I can just construct.
Yes.
But then how do I know this? The existence of that is alpha on all possible ordinals, and that's kind of too much.
You're constructing this from outside, and
Yes.
outside so you have your E here,
Yeah.
you have your set here, and you're just computing and then you have your formula here.
Yeah, that's true. But my assumption is that That's true, but my assumption is what? So probably I have to assume something more, or I have to prove something more for my complete thing, because what is complete? What is assumed to be complete, right? Complete means that all limits, co-limits, small limits, co-limits exist, and this is not small. And small is from the outside point of view, right? So that's fine. But probably. I guess we can solve it simply because if it is complete, probably we can prove that, okay, maybe not all limits exist, but all intersection of all subobjects exist simply because what? Okay, I don't know. Assume that we can do it, huh?
Well, okay. But can't you just, is it really bad to assume that the set is small?
That's the assumption, right? That you have a big universe or coevalent you have inaccessible. With that, of course, we can, but I'm trying to do it without any big assumption, and I don't know why. I have the feeling that we can, but I don't see how.
But then you cannot do it because if set is not small, then set is really not a model of set theory. So you're not assuming anything strong. So we know that you cannot prove that this exists, right? If you assume that set exists and
Yes.
it's small, then you're assuming consistency of ZFC, and you should be able to do whatever you want. But if you're
Not really. So if I assume just the consistency of ZFC, I cannot do whatever.
No, I'm saying if you start with the assumption
Yes.
that it's small,
Yes.
then you get the consistency of ZFC, and you should be able to prove more powers.
Yes.
Okay. If you don't do this, then set is just like some class, and it's trivial to come up with a class which is a model of ZFC. So you cannot.
No. Of course, but this is not that strong. So my point is that let's assume that we live in set even, right? You have some sort of set model. You are in set. You pick one object, then can you do class-like intersection of all subsets? Yes, I guess, right?
So if the Heyting algebra, the Heyting
Yes,
algebra is
yes.
small.
The Heyting algebra is
So
small.
can't you just pick from every class which are intersecting like
Yes, because okay, yes, that's the point. That's the point. That's the point. The point is that these guys are sub-objects of something, right? And that's no for each alpha, right? But some fixed thing, right? And that fixed thing, the number of sub-objects are not that big, right? It is set-like, and therefore, yes, you have a big class-like disjunction, but come on, it cannot be bigger than the disjunction on all possible subsets, right? So it's like in set theory. You are in set theory. You pick one set, and then let's say that you have a class-like indexed subsets of this. Of course, the intersection exists because it is just small, right? So that's the point, I guess. But anyway, so this is the trick. But the having unbounded quantifier is not the only problem. The main problem is actually something else. The main problem is when you want to interpret ZF is F. So you assume that your sets are well-founded somehow. But in topos theory, objects are sets, and we have no assumptions like that, right? Everything is just closed under some operations and nothing else. So there's no reason that everything is well-founded. You have to construct just the well-founded parts of the topos to model your ZF. And this is the way to do it, right? So constructing V, it is not just the only reason is not just handling the unbounded quantifiers. It is the main thing is actually handling the F, right? It is kind of right. So it assumes that any set with epsilon is well-founded.
Yeah, but I thought this is not the F in the F.
It is the F. It is the foundation, Frankel. Foundation. Huh? No?
It's Frankel, but
Yes, it's Frankel, and Frankel came up with foundation, I guess. Okay,
But it's not clear who came up with it.
foundation. Okay, so then foundation axiom, not Frankel, probably. Okay, so I whenever I want to construct some model of set theory inside using some topos, I construct my topos, but of course I won't go through this hell, right? To see that it really refutes it really refutes something and also validates something in set theory, like zero. So now maybe the CH. So you remember what is continuum hypothesis? Simply it says that you have n, you have the power set of n, and there is no cardinal in between, right? So this is just the next cardinal after n. And I want to prove that my ZFC cannot prove CH, right? And using this hell, you have to simply construct some sort of a topos, a complete topos, such that it validates C if you interpret C in a very reasonable way, and also it refutes CH, right? Again, very formally inside the language. I won't do everything formally inside the language, but you can simply see it somehow that the essence is there. So how to do it? How to do it? What's the idea? The idea is extremely simple. So you work with some B sets, right? For some B. And then there could be a very big gap here simply in B sets. So for n, I work with just n and equality. Equality is just usual equality. If two things are equal, one in B, otherwise zero. And Pn, the power set of n, according to B sets, is just the, all the maps from n to B. These are the subsets, right? The B subsets, if you like, right? Inside this topos, these are subsets. And come on, if I pick my B very, very, very big enough, there are so many functions here that I can interpret as subsets. And therefore, I can construct something extremely big as my Pn, right? And therefore, there may be something in between. So that's the idea. If you pick your B big enough, since it's not just n to 0, 1, it is n to B, then I have more options. I have more subsets. And if I have more subsets, then probably something is in between, right? Because I go just high. So the trick is simply this. So you pick some set X, whatever it is, and it should be just extremely big. So the cardinal say is, I don't know. So even X is just power set of n. So something very big, right? That you know that it is bigger than Pn, right? Pick it, whatever. I just care about the cardinal. And then what is the goal? The goal is that I want to construct a map of some monic map from X to, say, 2 to the n, right? And then I have so many power sets, right? If I construct that monic. But the problem is that, of course, I cannot do it, right? Because we live inside the model of set theory that we have, right? And I assume that we are living in a model that probably CH is true. So I don't know, right? I don't have this much subsets. But I have the approximations of it. So any function like this is just something like this, right? It
Don't exclude the power set of n, right? Because power set of n.
is strictly bigger than power set of n.
Yeah.
So then you cannot have a monic map, right? This is monic. So you cannot have a monic map from Ppn to Pn because you have more elements here.
Like, how can I get money
No, you cannot. This is what I'm saying. You cannot do this. Right? This is just kind of impossible. So, but I want it. It is impossible, but I want it. Right? So let's just put this n here, and then this function is equivalent to have a function like this with some conditions to be monic, right? So what I'm saying is that there is no function like this, but the finite approximations of it should exist. Why not? Right? Because there is no contradiction there. Finite approximations are these subsets. What do I mean by that? I mean this. So let's be just somehow formal. I want to construct some B, then see that in B sets, this is just very bigger than that, right? So what is my B? First, what is my P? So P is just the set of all finite finite partial functions from x times n to 0, 1. You pick some subset here, finite. You assign 0 or 1, functional in a functional way, and that's it. You pick all. And there is order. The order is that the function p is less than the function q if q is just bigger, right? P is the restriction of q, right? So this is my poset. So I have some, say, think like this, that you have finite subsets here and you get it bigger, finite functions, and you get it bigger, 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 bigger. Never you get the whole function because it doesn't exist. But all the approximations probably you get, right? It is something like that. Let's say that you live in rational numbers. Then the square root of 2 does not exist. But any approximation of it, any better and better approximation of it exists. So you pick all of them. And if you want to understand from the point of q your square root of 2, then you say that it is a limit of these existing things. So what I'm doing is kind of the equivalent of that. I have the partial realizations of the thing. And then my h would be offsets of p and order. So we saw that this guy, offsets always is some Heyting algebra, complete Heyting algebra. For any complete Heyting algebra, if you pick just the u's such that the negation u is u, it would be Boolean. I have to force everything to be Boolean because, you know, I need something classical. So that is just the classical obvious force to make everything classical. Otherwise, I don't need it, kind of. Probably one thing that I have to mention is that how to compute this guy. So P is in negation u. If for any q bigger than p, there exists r bigger than q such that r is in u. That's the computation of negation u. So you remember that negation of offset is defined like that everything above the guy is not in u, and then if you open up twice, then you see you have this. People usually call this the density condition, right? Enforcing arguments. But you have it simply because I want to make everything in classical in obvious way. Okay, so that is my B. It is a perfect Boolean thing. And then what I want to do for now is this, that I want to construct For any, say, x in X, I want to construct some what Rx as a sub-object of N, therefore as a map from N to B, right? And in an injective way, meaning that I want to say that for any element in X, I have a distinguished subset of N, subset in terms of P sets. And since X is just very big, therefore I have so many sub objects, right? That's the idea. How to do this? So for any X, assign this. So this should be a map. So therefore Rx of N must be something in B. It should be some offset with some stability condition, right? Pick all P's such that Pxn is 1. So the value of N is all possible approximations that believes that you get 1, right? So more or less I'm saying that, like, you know, you don't get it, right? But it is simply equivalent to all possible, you know, approximations of it. First thing that I have to prove is that this is offset, and which means that it lives in H and also it lives here, so it is double negation stable. It is offset because if you go from P to Q, which is bigger, if something is 1, then it remains 1 in the bigger function, right? So a function, you know, Q is bigger than P if the restriction of Q, the domain of P is P. So that's obvious. The non-obvious thing probably is this, that you have this condition. So assume that P is in double negation U, and I have to show that it is actually in U. If P is in double negation U, then for any Q bigger than P, there exists R bigger than Q, such that R is in U, meaning that R xn is 1. And I want to show that P of xn is already 1. So I'm saying that if you have P here, if for any Q above, you get some R above it, such that you get 1. Therefore, I'm simply saying that there is a bar here, you know, intersecting with all possible way to go up. And here on this bar, always you get xn 1. And then if it is the case, then you have to have your xn1 at the beginning. That is the thing that I want to prove. So either Pxn is 0 or it is undefined, right? If it is 0, then it is 0 upward, always. And that's just a contradiction with this, right? Because it simply says that if you go high above, you hit 1 at some point. If you are 0, then it is impossible. So maybe it is undefined then, right? If it is undefined, then there is no reason to hit 1, simply because I can extend it from P to Q with assigning 0 to it. And when I assign 0, then never above you can get 1, right? Yes? Do you get it? So it should be 1 really. It should be forced to 1. You have to pick it as 1 at P, because otherwise, if it is 0, then 0 everywhere. It cannot be 1. If it is non-defined, just define it one step above as 0. Why not? There's no contradiction. I can do it. And then when I pick 0, then that's bad, because up I cannot pick 1. So this means that this condition is double negation stable, right? If something is in the future on some bar is 1, it's always 1 at the beginning. So the whole point is that now I have really a well-defined sub-object, right? The only thing that I have to show is that these sub-objects are different for different x's, and the proof is just easy. and too easy actually. The proof is this. So pick some x and some y that are not the same. Then Rx is not Ry. To prove that they are not the same thing, it is just enough to find one n such that, you know, P of xn for some P is 1, and, you know, Pyn is 0. Right? And of course I can do this, right? Just pick any n. That's easy. But it is too easy, right? It's just too easy. So it does not say that n should depend somehow on something, you know, any n and 0, right? And P as just 1 on x, y on, you know, that's just too easy. And there is a reason for that, but I won't say anything about for the moment. So therefore, the cardinal of x is less than the cardinal of, you know, B subsets of n, which means that this guy is bigger than, you know, 2 to 2 aleph naught, because x was ppn, or just something very big. And since this guy is extremely big, you can just get something in between 2 to the aleph 0, right, in between. So there is a serious lie in my proof, and the serious lie is the last step. Maybe the first lie is that this is not a proof of independence, because the proof of independence is when you really construct the model of set theory, you check all the axioms, etc. And then also you check the CH as the axiom and you show that it is wrong. I didn't do that, right? I said that, come on, everything is fine via that trick. Just construct the topos. That's true. The second lie, the first lie is not that serious. If you do it, you get it. So I just constructed the topos structure. The second is really a lie. Because what? Because, yes, this inequality between cardinals is true, but it lives outside of my set theory, right? I have to prove that the cardinal in terms of B sets is bigger than the cardinal of n, again in terms of B sets, and this inequality lives inside B sets, right? This lives outside, and that is just bad, right? Because who says that the notion of cardinal is kind of absolute for these things? And that's the whole point of the whole game. That's the bad thing. But the construction is right, and later when we see the sheaf things, I write the correct version of that. It is not just far from this. So the only thing that you have to prove is that you have to actually show that you have to first interpret x as some b sets, x the set as some b set. Then you have to go from this guy to, you know, say omega to n, and then you have to show that this map is monique, but it is not enough. Then you have to pick something else, tweak something, and then you can prove it. So it's not that far from truth. And being monique inside is the main thing, right? This is monique outside that we showed. And this is the reason that this guy is too simple. But, and we will see it later. But the main point is just simple. So the point is that if I change my viewpoint from truth and falsity to different values in some Boolean algebra, then I get more values, therefore I get more subsets, and therefore I change the notion of subset. And therefore, probably it is obvious that whatever you say non-trivial about subsets in set theory, I can just change it. There's a theorem actually about that says that, you know, there are two things that you can know about power set, the size of power set. that I forgot the name or even of the theorem. But there are some very basic things. One is to the the cardinal is bigger than blah blah. No, that's kind of very obvious. No, the theorem is just a very important theorem, very deep, that selects two properties and then says that any function that has these two properties, any function, a theoretical kind of function on the class, can be the cardinal of the power set. So more or less, we know nothing about the cardinal of power set except some very basic things. And this is the reason, right? Because I can just simply change it in any way that I want, more or less, in terms of size. So of course we know nothing, because we know nothing about the Boolean algebra, because you can change it. Also, it says that it is important that you think more than truth or falsity, right? Having the Boolean algebra, yes, after killing everything by one ultra filter, you can get it back, but you can get the first order part back. If you want to get your new set theory, it is really important at what kind of Boolean algebra you use and what size of it, right? So that's not a good practice to just force everything to be usual truth and falsity kind of things. So that is my CH. We will see the real CH via sheets later. The part that I couldn't prove was, and I will next time, that I open of R. So this is arithmetic, add some relation R, some binary relation R, use open formulas for that, and that guy cannot prove the pigeonhole principle for R. And to prove it, I kind of use exactly the same construction via some tweaks, which is kind of cool. And this is more or less so this is coinversing, right? In terms of Boolean valued models, more Solovay like, more Scott like, and then so the same kind of argument with, of course, some tweaks works for this guy, which one could call forcing for arithmetic. We will see this guy later, and then we move to another construction of the process. Sure. Yes, this is just for simplicity, but yeah. So the full guy. So my hope is that my proof, which is just the Paris-Wilkie changed a bit, is kind of conceptually simpler, simply because I allow using Boolean algebras, and I don't force myself to be true or false. Exactly the same proof with less, non-canonical choices here and there, but still the same.
But you can skip the top.
The point is that the model lives in some, it's a B set, right? So it lives in B sets. So you can present it as some, B set Boolean value things. But the point is that conceptually, you can think like that I'm actually interpreting arithmetic inside the topos of B sets for some B, right? Any other questions?
There's no problem with, for example,
I guess not. Yes. But it's just a matter of presentation, right? The essence is simply just there.
once you can do this with the process, then you don't have to worry about you don't have to define, I don't know, density or then subsets or constants for this model of theoretic forcing. You just get it for free because you already defined logic on everything.
Yes. The logical part you get for free, but the non-logical, of course, changes this or that way. My hope at some point would be that we have actually some forcing theory for arithmetic, that for some toposes or some categories like toposes that we defined, you get not for free just the logic, but also the arithmetic of some kind, and then the rest is the part that you have to do, right? Let's say that you get some very basic, you get, let's say that I design some arithmetical toposes or something, where you get some canonical choice for your n, right? Or some, not just one. And in a way that whatever your topos construction or your arithmetical topos construction is, always you validate some sort of induction or something. And therefore, the setting, the general setting is there. You have to change your B, your everything to get, independence results.
Okay, so
But it should not be that easy. But one important point, probably now it's time to mention it, is that the best kind of forcing that we have is Yon's forcing with random variable machinery, right? And more or less, it is this. So for not any B, he picks B as some finite subsets of some definable finite subset of some set, non-standard, etc. And then it is B set, right? So more or less, we can say that Yon found a very sophisticated way to use this topos to interpret arithmetic. But there are more toposes than this, than B sets. There are the full sheaf toposes that could do something for us. These are just the local sheaves, right? These are sheaves over B, but probably there are more. But even better, there are more effective kind of toposes that are kind of better in terms of computation. We didn't even capture that with this machinery.
okay, but there should be some, for some arithmetical forcings, there's completeness, right? So you don't have to look for anything else. You could just look for like something like.
Yes. So technically, even for this, there is one, right? There is one that says that, say, here you have PV, for instance, and then for all PV, these are enough, right? For any model, it can be embedded here. But it kind of means nothing, because even in set, we don't need this, right? In set, we have completeness. We have Gödel's completeness. That doesn't mean anything, because yes, there are enough models, but you have to find it. You have to see a good machinery to naturally find them, and probably you cannot find them here, but you can find them there. For instance, it is possible using B sets to prove the failure of axiom of choice. But of course, always these toposes validate the axiom of choice. Therefore, you cannot pick the whole thing. You can pick the sub topos of this somehow, right? But if you use sheaves, there is one canonical way to refute the axiom of choice without any tweak or any tricks, right? So that's the point. The point is epistemical, that can we see it really or not. Thank you.